Morning, everyone. How are you? I know everybody's. I'm a little intense sounding. Can I be less of the word of God and more like the word of your favorite uncle? Let's try that. Awfully formal sounding uncle. Oopsie. I also don't want to stand behind the podium, so how about here? All right for everybody? Excellent. So really got to be here, and as Jules said, we'll be talking about sort of change and how to actually use Spark to deal with change. And the two different types of workloads that we deal with are typically data engineering workloads, which you sort of figure out how they work, and then once you set them up, they run 24/7 for hopefully a very long time without changing, if we've done our job right. And there's data science workloads, and those tend to work quite differently, right? If you were at the Spark Summit last year, you would have heard me talk about goal-based data production, which is more of a how do you deal with ad hoc queries and ad hoc data production in a very productive way when bringing the business users in. So again, a lot of what we do is productivity oriented. And the reason why we do that is because my company has a very small, highly leveraged team, but we have just obscene amounts of data. We do with petabytes of data, and not only is it long, but the data is also very wide. We deal with thousands of columns because we operate some very complex systems. We deal with patient level data for 300 million people in the US. We have to process it in a privacy safe manner. We do just a ton of automated machine learning and AI over that. And so it's really important to get the teams productive and to find patterns for repeating work and for making things better in a very complex environment, an environment with a lot of change. So, as a famous saying, there's two things you don't want to see in the making: sausage and whatever the thing that comes. And I will claim, after having spent a lot of time analyzing how exploratory data science works, for the purpose of making our data science team super productive, that you most definitely do not want to see exploratory data science in the making. See, there's this myth we have that, exploratory data science is all these beautiful data flows and pipelines. If you just set them up the right way, it all works wonderfully. This is just a picture from an IBM paper on how to use semantic graphs for describing data science processing. And I have nothing against the paper. It's a great paper, actually. And I have nothing against precise description of machine learning pipelines, but this is a myth. This is the end result, right? This is the way the sausage tastes. This isn't the making of the sausage. The making of the sausage looks something like this. I just zoomed in on one area of the graph where there's a k-means clustering with this magic constant 4. How do we decide to have 4 clusters come out of k-means? Well, we probably decided by trying a bunch of different things. We tried it with more clusters and turned out it's too slow to train because k-means is a very expensive algorithm. And then we tried with too few and it didn't differentiate enough. And we did some type of search process. And eventually, we decided on 4. Is 4 the optimal number? Who the hell knows? But the data scientist doing the work decided that that's a good stopping point, right? So realistically speaking, if we look at exploratory data science, it's really a process. It's a search process. It's an ill-defined search process, and then it has very fuzzy termination criteria. And what it's driven by is essentially the output of the previous few operations we ran, right? You grab a sample of the data, you do some analysis on it, maybe you do some training, you run cross-validation, you do some visualization, you go, this works well, this doesn't, let me try something else, and repeat, right? How many of you here are on the data science side of the house versus the data engineering or developer side of the house? Data science? Data engineering? All right, good. Because this talk is about you guys and how you can make your data scientists a lot more productive, because fundamentally you do not get it. The Spark committers don't get it. Most Spark committers are not data scientists, and even the ones that know something about machine learning don't spend their days using Spark. So what I most want you to do is actually develop empathy for the people you're hacking data, typically notebook environments, all day long. They don't use IDEs. They don't deploy in jars. Well, eventually, after exploratory data science is done, they might. But during the process, they do not. What it actually looks like is a tree, but not like a computer science tree that has a pretty fixed branching order. No, it looks like a natural tree. It's all gnarly and, very, very organic. I'll kind of start doing the same things. I mean, typically there's some production data with tables that are very large, and you often begin by grabbing some samples of it, and then based on whatever task you're solving, you go about, essentially branching. So if you think about any kind of branch point in the tree, you can think of it as a notebook cell evaluation. Zeppelin notebook, Jupyter notebook, Databricks notebook. Data scientists like working in notebooks. They don't like using REPL. They most definitely don't like using IDEs. And you can think about backtracking as code modification, right? I was sampling at 1%. Well, gee, why? Well, because it's fast and because I wanted to test my code. But 1% sample is too small, so now I need to sample at 10%. Is that going to be enough? Or do I need to sample at 20%? I tried these features, but they're kind of good this way, but they kind of suck that way. Let me try another set of features. Let me try different featureization. This constant backtracking is this exploration process, again, driven by what we learn. And so a key point here is the backtracking changes the Spark plans. How many of you are familiar with what Spark plans are? Spark plans describe what Spark is going to do. If you think of it, it's like the abstract syntax tree of a compiler before it generates code. It's the abstract syntax tree of a SQL plan before the database starts optimizing and executing it. It basically describes the set of operations that are going to be performed, right? And that's a problem because imagine that you had to write code or build frameworks to support somebody who constantly changed their code. If you want to think like a developer who basically redeployed their jars every few minutes. Do you know developer tooling that can do this well? You don't, because it doesn't exist. The closest is a traditional application server with dynamic loading, when you sort of have a reload on save. Spark actually doesn't do that. Although Spark does a lot of work with class loaders, Spark does not have any of the typical smarts that a, say, J2 application server has on dynamic reloading of an updated application, which causes problems. Backtracking is really not easy. So you basically have two options, right? You have the option of constantly changing the code in the notebook cells you had, and then you lose your previous state, and we'll see why that's a problem in a moment. Or you have the reuse by cut and paste, which is usually the favorite approach of data scientists. So you end up with things like, you start with a variable called df for data frame, and then it becomes df1, 2, 3, 7. I've seen things like, df17 join, dimension x12. It's like, by the end of it, you're going, what is going on? You have to scroll back and forth. Don't forget that the notebook environments run in browsers. If you look at the JavaScript, it actually kind of sucks. It's very, very heavy. So if you end up with a very long notebook with all this cut and pasting, your browser starts really slowing down. It's a fundamental problem. The other issue is, we can look at the tree for an individual's workflow, but you can also look at it for a team's workflow. And it looks exactly the same way. Just overlay the individual workflows together onto the same logical tree, right? Spark by itself has absolutely no team support in it. But data science teams working on the same production data very often begin work in the same way. Again, the typical ways, I will sample key production data sources, or I'll create cuts and snapshots of them to get into a safe data science environment before I start messing with it. Right? So fundamentally, there are a lot of opportunities for caching, because in this tree view, the thicker the branch, the more people on the team, or the more times the same people on the team are going to reuse whatever piece of data production is at that node. Again, querying, featureizing, and building MA pipelines, it's all the same thing. It's all essentially data production. It's data transformations, right? We use different APIs for them, but they're exactly the same thing. The only thing that's different is model training, but actually the easiest part of the thing, because it's a black box. You parameterize it, but fundamentally, you hand off something to the training and some numbers come out. There have been studies on what data scientists do, and 80 to 90% of the time is spent on mucking around with data as opposed to actually training. When it's training, data scientists go get coffee, or more like go on vacation in some cases, depending on the size of data you're training and the complexity of models. So the fundamental tool data scientists have is essentially caching. right? Because I'm going to use this data, I'm going to use it for a bit, I don't know how long I'm going to use it for. This isn't really a formal production environment when you know some intermediate aggregate is going to get built and then a specific set of reports or analysis is going to be built or specific models are going to get trained off of it. This is all exploratory. And there are a lot of problems with what Spark has. So first, caching works on a single cluster only. And if you look at the implementation, there's cluster-specific IDs, and the JVM ID of the instance of the JVM is a GUID, which is actually part of how cache plans are, which also means that if you restart your cluster, which happens very often if you push a cluster past its limit due to out-of-memory issues, you just simply spot instance churn. If you're using the cloud and trying to use lower cost, you lose all your cache data. That could be data that took many hours to produce, or tens of hours to produce. So that's kind of a problem. The only way to free the cache is to actually call unpersist. But to call unpersist, you need to have the exact plan, think of it as the exact data frame or data set that you called cache on. But if we don't do the reuse by cut and paste, where we have, DF15, you actually don't have that plan, so you can't actually unpersist. You can't uncache the thing. You can't free up your resource, which is one of the reasons why exploratory clusters tend to die with much higher frequency than production clusters. And by the way, if you do have the DF15 thing and your session detaches, you have another problem, because sometimes the way data scientists code, you don't even know what order of execution you should run your cells in your notebook to not create negative side effects, to actually get DF15 to be live, to be unpersisted. Okay? And last but not least, there are no dependency checks. If any of you have had experience doing caching, which most data engineers don't, because data engineers work in predictive environments, you'd notice that sometimes you get served stale data. We don't want to get served stale data, and you have very little control over that. So how do we fix this problem? Well, the ideal exploratory environment needs to do several different things, right? It needs to work cross-cluster, because very often machine learning stresses clusters to the max. If you start training, you're going to busy up the CPU on the cluster at 80 to 100% for very long periods of time. So essentially, it's difficult to have multi-use data science, exploratory data science clusters, especially since you often don't know when you're going to start training. I mean, initially, when you're doing querying, you could share the cluster, but at the point at which somebody starts training, if it's a shared cluster, you're stuck in one of two options. Either training takes longer, or the other people don't get to run anything. Right? So data scientists like to use a lot of clusters. You don't have to worry about the whole saving, updating, etc. You want it to work like cache, right? When you say dataframe.cache, you don't have to think about where is it caching. If it's persisting to disk, where exactly is it being saved? Well, you just want it to work. But you also don't want to worry about deleting and freeing up resources. You just, as a data science, you don't care about this thing. You just want it to happen. It's not the problem you're trying to solve. You're trying to figure out how to train a model. And last but not least, it's important to have tunable control over how fresh or stale the data you work with is, right? Sometimes it's really important to work with very, very fresh data. And sometimes you don't care if the data is a week old, right? And if you don't care, we could use that. Right? We could use that to do less work, to share more data across the team, to share previously produced results. Right? So the way we solve this, we need three things which we don't get from Spark. Right? We need what we call configuration address production, which logically works kind of like caching does, which is essentially I look at what your plan is, and I figure out how to persist and manage the data based on that. You change your plan one bit, you change your sampling seed from 0 to 1, it's a different plan, it's a different piece of data, I need to produce it. Or if I have it, I'll give it to you, right? There's no pathing, there's no table management. Just imagine you're manually choosing to persist, and you're going to say persist to tables. So you do your plan, and then you say, dot write, dot save as table, my experiment 1. Okay, great. Let's say you're sampling. Now you want to change the sampling rate from 10% to 20%. Well, if you override the table you've written, if you ever want to go back to 10%, you lost your data, so you probably don't want to do that. So you go my sample table 2. Then you want to change something else. You filter the data differently. Oh, I want to exclude nulls in this thing because they're polluting my data. I want to replace all nulls with zeros in this column. Now it's sample data 3. So before you know it, you're like, I forget what is 2 and what's 3. Now comments start popping up in your notebook to tell you all the different versions of your tables. Before you know it, you start saying, well, let me just put the things that I'm changing the plan on into the table name. So it becomes my data sample rate 0.2, and then the first thing you get is an error because your sampling rate is a floating point, so it's going to be a dot in your database name, in your table name, which is going to be interpreted as a database dot table name. So then you start encoding things, and it just gets completely out of hand very, very quickly. And last but not least, we're going to do this dependency management thing, right? We want to create a user-level mechanism for somebody working with Spark to express their preference on how fresh or stale the data is. And we just want it to work. So how does this happen? Well, in our case, you replace dataframe.cache with dataframe.capcache, and it just works. We're planning on open sourcing all this into a new library that we sort of been trying to get to release, but our standards are pretty high to take the commitment to support something. So, and there's some interesting changes coming in Spark 2.4, particularly around the data source API. So we're holding off to make sure our APIs still hold well. But it will come out. So if you pop over there, click watch on GitHub, and you'll be notified when we actually ship it. So let's take a look at an example. Very, very common use case. I guess I'm trying to pick the simplest thing that fits in very, very zoomed in screens in notebooks so we can walk through it, right? Is the classic resampling problem. Like you have some big production table. It's too big to process. You want to do a sample from it. But because you don't want to end up with outliers in a sample that twist your data, what you typically do if you say want to look at some statistics, analytics, or even do machine learning training, you don't do it once on the sample, but instead you do resampling. You pull many subsamples of that. So now say if you want to compute a mean or a count rather than having a single value that you can't reason about, you'd have a distribution of values, right? Does that make sense? Then often there's some enrichment process going on, right? Often production data has things like just IDs for various things we care about, transaction IDs, customer IDs, etc. We have other tables that we want to join the data in to understand which customer is this, which transaction is that. So you do a join, then some additional filtering analytics to get sort of the data you would then do data science-y things on, right? Really, really basic use case. Almost every data scientist working with production data that's large has to go through this. So I try to think of the simplest possible example with like one column data. So let's ask this question. Prime numbers are interesting. So let's see if we take prime numbers modulo 10,000, whether they become interesting numbers. What's an interesting number? Well, actually, crazy people on the internet have assembled data about what are interesting numbers. So I found this table with for every natural number between 0 and 10,000, a note on whether it was interesting or not. Turns out about 50% of the numbers between 0 and 10,000 are interesting in some way to mathematicians who are just darling. And so we have our primes table, and we have this table of interesting numbers, and we just want to sample, subsample, join, and maybe just look at the rate of interesting primes modulo 10,000, right? So how will this work? We'll grab our data, we get the interesting numbers, right? We get the primes, we set a limit of 10,000. We do a really, really simple sample. We sample at 10%. We set the seed so it's reproducible. Then we want to resample, calculate the stats in union. So we'll do it, say, 30 times. We grab the sample, turn the prime into n, which is our join column for interesting numbers. We resample. We want to vary the seed for every sample, otherwise we're going to end up with the same data for every resampling, right? We take the distinct values because we don't want to multi-count once we modulo 10,000. Just grab the last 4 digits if you want to think of it. Join our interesting numbers table on n, inner join on n, and then save the sample number in the data so we know what produced what, and let's just count how many interesting things they are as the count of n's, right? And we'll display it, you know, percentage of numbers that are interesting. Does that make sense? Absolutely, you know, nothing fancy, very, very simple data production. So if we want to cache, there's really two levels where we want to cache, right? We certainly want to cache the first sample, but then we're also doing this resampling thing, and we may vary how we resample. The number of samples we create, the sampling rates, sometimes data scientists even check the seed stability, because sometimes the seed just gives you odd data. So you probably want to cache the large sample, and you want to cache the individual subsamples. They're tiny data frames, they're single row data frames, because we're just reducing them to counts, right? Everybody with me? All right, cool. Let's do the thing you're not supposed to do, which is a live demo over the internet. The best platform for interactive work with Spark is actually Databricks. I'm not paid to say that. It just is a fact, and trust me, we evaluated options. So I ran this on Spark Summit 1, and I ran this early last night at 3 a.m. and it produced some results. So I sampled the data, I sampled the primes at 10%, I cached it, I computed some stats, blah, 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 and I displayed a box plot of interesting primes, right? Because I was lazy initially, I computed just 3 samples, right? And then I even detached this notebook on cluster 1. Now this is done. So now today, somebody else on my team pops up, working on a different cluster, Spark Summit 2, and you know, they go for the same motion, because again, if you remember the tree, on a team in a single production environment, many people end up beginning their work the same way, and then their work often forks in completely different directions, both because they want to solve a different problem, but also because they're just different people, and there's no sort of, you know, there's a lot of art to data science. It's not just science. So I'll grab the data, and now, you know, 10% is a common sampling rate, right? 0 is a common seed. We just hit this, and we get a result immediately. Now, this is interesting because cache is actually an action, meaning it needs to check whether the data is produced, and if it's not, it needs to produce it and cache it. Cache in Spark works slightly different ways, but it is magically hooked up into Spark in ways that are just not possible to do from the outside right now, which is one of Spark problems. So right here, we actually got the benefit of the 3 a.m. production I did on a completely different cluster. And now let's say that this person does a similar sampling, but this time they actually want to go to 5, right? As opposed to the 3 I did before. So let's see what happens. Spark is doing a bunch of things behind the scenes. And again, this is going to run relatively quickly here because the data is small and have small clusters, but you know, in production environment, these sampling operations could be taking literally hours, and many of ours do take hours. So we ran only 2 jobs, even though we built 5 samples. We actually automatically reused the 3 subsamples that were built with exactly the same plan. If the plan was different here, we wouldn't have. But again, when you have shared code on a team, shared functions, libraries, and many people end up using pieces of the same stuff. Now, what is an important thing here? The 2 people, I'm Gemini, so the half of me that did this work at 3 a.m. and the half of me that's doing the work now in front of you, we didn't need to have a meeting to talk about how we were going to share data production code and agree on table names and paths we were selling the data. It just happened completely automatically, right? And that's one of the benefits we want. We want this productivity increase to happen without a lot of extra communication and syncing and meetings and so on and so forth. And here I may just want to produce, you know, no box plot, but maybe I just want to see the table. Okay? So now, in the real world, our production data changes all the time. So here I'm going to simulate a change from a different cluster, Spark Summit 3. I'm going to simulate the change to the production table. I copied it, and I'm literally going to overwrite it right now, just to make sure it is fresh. And while this is happening, let's say that the person is wondering, gee, you know, what would happen if I actually sampled at a 25% rate? You know, maybe 10% is too little. Maybe I'm missing interesting data points. Right, let's see if this completed. It did. So, say, you know, I changed my plan, right? Rather than going sample 1, sample 2, sample 3, I'm choosing the strategy of just changing my code here. And if I run this, what would you expect to happen? Well, yes, it kind of depends on intent, right? Maybe I'm okay with not picking up new data, or maybe I'm not. If I haven't expressed my desire, I think we had a table refresh issue. Did we? Spark caches table metadata, which means it caches the files where tables are. And I did not use Databricks Delta because I didn't want to have a Databricks specific demo. And I think caching just picked up. Let's just refresh the table. This would not happen all the time, which is one of the issues with refresh table primes, which is one of the issues that creates problem for data scientists because you often don't know that something has changed. Let's do that again. And we built it. We actually changed the plan, right? So you change the plan, you automatically use the same data, meaning the new data, because the cache had not picked up. Well, let's see what happens if we were rerunning this command with exactly the old plan that we had cached at 10%. It says, wow, illegal state exception. The cap table, and some very, very long thing, it's stale because some of its dependencies have changed. Default primes has changed at this date and time. So it essentially is warning us saying, hey, look, you know, I could reuse a piece of data that has already been generated, but I don't know whether this is okay with you because the thing that the data is based on has actually moved on. And you have not expressed your preferences on what to do about this situation. Well, typically, if you're a data scientist, you kind of know how much or little change you're willing to bear, and what I hid is I didn't run a cell that one of a data scientists would typically run, which in this case would set a setting to describe, you know, how fresh data you care about. In this case, I care about a day, right? Now let's see what happens if I do that. It'll be perfectly happy to grab and reuse the data. And freshness can be overwritten on a per data frame production, and so on and so forth. There are lots and lots of controls, right? So this is the environment you want. You just express your preferences, and then everything else just works magically, regardless of who does the work, when they do the work, what cluster they're on, do they all do it at the same time or not at the same time, right? This is the way data scientists wish cache worked. Cache really is designed for data engineers. The data engineers never want to use it because they typically you know, produce things in a very defined forward motion in data flows. So we don't have time to go for a lot of the details behind the curtain, but fundamentally, these plans, they have representations, right? So you can take the representation, you can cross-cluster canonicalize it. You can make, essentially, you can make things that don't matter across clusters be changed. And you can then compute a secure hash of that. And that essentially becomes the ID of the data. If the plan changes by the tiniest bit that matters, because there's a bunch of changes that don't matter, right? If you say x less than y versus y greater than or equal x, they're the same thing, they don't matter. So you want to produce the same hash for those. But if you change the sampling rate from 10% to 20%, You want it to matter. You can also capture creation times and any settings related to expiration. And you can actually look at the plan as you're writing when you have the live data frame with all the dependencies and actually persist information next to the data about which data it depends on. And then you have a graph of dependencies you can make decisions on. And without going into the details that we don't have time to, because this is not a deep dive session, fundamentally we had to rebuild the entire set of data reading and writing APIs to Spark to allow for the extensibility that's needed to do this. Reading API is inconsistent. The writing API of Spark is inconsistent. The user level one, the internal API is actually much cleaner, but the user level ones are not. There's two implicit authorities in Spark. The one where you do manage tables, and the one where it's sort of like, hey, you're on your own, just write to whatever path you want. And we made authorities first-class objects. So cap is an authority. It manages how data is written. And so you give it a plan, and you don't need to give it a path or table name. You just say, okay, I got it. You know, I'll manage the data and the metadata for this. And last but not least, we introduced the notion of interceptors that can watch over reading and writing and provide sort of orthogonal services. Some of you are familiar with aspect-oriented programming. It's sort of a similar technique, but tied to a specific API here. And that's how dependency management is tracked. Because the only time you know the dependencies is when you have a live plan to write. Once you've written the data, you've lost all the dependency info. So Spark actually throws away tons of valuable information by default when it writes data, which is frankly very, very bad. So this is the basic idea. The basic idea is that as engineers, you have a huge amount of power to radically improve the productivity of your data science teams. But you have to start understanding their workflows, and you have to start developing empathy about the way they work, because data scientists work nothing like data engineers. Thank you so much. I'd love to take some questions.
Thank you, Sim. Unfortunately, we're out of time, so we can't really take any questions. But Sim is going to be around outside because we have to get another speaker in. But give a big hand to Sim again one more time.
Thank you, everyone.
Thank you.